This is the second lecture of week 2, and today I will be starting the element types which are known as beam elements. So on the agenda today, we have the following items. First, I will remind you of what the problem chapter, earlier chapter was, the bent rod, analysis of bent rod. But this time, we're going to be solving that with beam problems, which is essentially chapter 7 of the textbook. And then I talked about roll-up orientation point when the cross-section is non-circular or non-tubular. And look at a few things about different cross-sections and how it affects B, is needed to do C. And finally, time permitting, and we'll see how it goes, I'll show you how to make sure that there is a point that is imposed in the mesh of a beam. Okay, so let's go ahead back here. And the problem that I want to do for you later, after talk a little bit about beam elements, is this problem that we did. I believe it was chapter 2, the very first problem that I actually solved. However, there I modeled this thing entirely with solid element or tetrahedral elements. When you have a structure that's slender in one direction, in all likelihood, it's just about impossible to do it with solid elements or tetrahedral elements unless you have a lot of them, which is not needed. Or I mentioned earlier that if you take the analysis of a frame of a high-rise, there are thousands of I-beams and different type of element cross-sections that are involved, mostly I-beams. And it's impossible to solve that whole thing as a set of tetrahedral elements in all these 1,000, for example, I-beams. So the whole idea behind a beam element is that you represent the geometry with a wireframe. For example, that bent rod. This is the center line of that bent rod or curve, center curve of that bent rod, and the cross section happens to be circular. The dimensions are all given in that chapter, and it's written on the right hand side. And we have taken this top point. The bottom point is clamped. That's how we did it. And the top point on the right-hand side is actually loaded. There's a concentrated force acting on it. So in a situation like this, you take the wireframe and break it up into elements, beam elements, and beam elements come in two varieties. One is two-noded, they're called linear beam element, or and the other one is parabolic or three-noded, okay? So what you see here is, for example, is it looks like these are two-noded element. There is an element here, and it's got at the two extreme ends two nodes. So these are linear elements. And okay, so that's what we're going to do. It's a lot easier to put these things on a wireframe than to take a three-dimensional representation of this bent rod and then break it up into tetrahedral elements. It's unnecessary. Now, the way the beam elements work is that, for example, here I've shown you a linear beam element, so it goes between two nodes. At each node, you have 6 degrees of freedom, 3 translation and 3 rotation. Let me remind you, for tetrahedral elements, each node has 3 degrees of freedom, 3 translation, and rotation was not part of the deal in the part of the degrees of freedom in a conventional tetrahedral element, solid element, okay? But beam elements, each node has 6 degrees of freedom that has to be accounted for. Now, this business of orientation point becomes clear in the next slide. However, I want to tell you here, if you take a beam element with a circular cross-section or a tubular cross-section, it doesn't matter how you kind of oriented in space as far as a rotation is concerned. But if the cross section is not circular or tubular, then the response of the beam, for example, in this cantilever beam, depends on how this beam is oriented in space, because all we do is we draw a line. So we have to say how the cross section looks like, and specifically what the orientation of that cross section is. Notice that for a cylinder, it doesn't matter if you turn this cylindrical beam maybe rotated 90 degrees about its axis, it behaves exactly the same way as the original one, but this one does not. Okay, so that's what I meant when I talked orientation point. That's very critical when the cross section is non-circular. This one is circular, so we're not going to worry about it. Now, the way these beam problems work is that you take the wireframe, create the wireframe, and do not forget, once you create this wireframe, to join it. Okay, even whether in a sketch or you do actually uh, particularly in Sketch, okay, because if it's a wireframe in space, it could be that you can actually measure it. However, if they're not joined at the place where the two uh, uh, 3D curves come together, there's going to be double nodes, okay, and you have to handle that later on. But if you join it, then there won't be those double nodes that are created. So for now, let's not worry about it. This is a planar curve, so I'm going to do it in Sketch, and I'm going to join it. The dimensions are all given here. This is 8 and 5 and 1. So let's go ahead and do that. First, I'm going to create a part, and immediately I will save it. So File, Save Management. This is going to be Save As. Desktop, new folder, and I'm going to call this thing bent rod with beams. Bent rod with beams, with beam elements. Okay, so everything is going to go in there. Now I'm going to create that. Notice that you can be in part design. So let me actually go to the part design. That's what we have been doing for the past week or so. So on that vertical plane, I will sketch that wireframe basically, which looks actually something like that. For example, I'm going to dimension these things. I believe the distance from here to here, I think that was 5 inches. Let's check that one more time. Yeah, 5 inches. You can see that this distance is 5. So I'm going to double click on this. My units have already been changed. 5 inches. I'm using imperial units here. Okay. And then the distance from there to there is 8 inches. Okay. And the radius of this bend is 1 inch. So that radius is 1 inch. Very good. Exit. Now notice that once you create this wireframe, as a sketch I've done it here, do not forget to join this. Because if you do not join it, you will not be able to essentially define material properties on it. So what do I mean by join? Join is not something that you find in part design. So I'm going to switch to, for example, I go to generative shape design. You can either go to wireframe and surface design, that's one option, or you can go to the more sophisticated version of it, which is generative shape design, which is down here. The join operation can be found in either one of those two. It makes no difference. So just to make your job easier, at least today, I'm going to go to Start, Mechanical Design, and Wireframe and Surface Design. All I need is that join operation. You see that? Under the operations toolbar, this is the toolbar, one of the main operations, one of the main toolbars, there is a join here. Okay, you click on that, you click on the join, you select this, and you say okay, and don't worry about it. Okay, don't worry about it means that you don't see any change except that join is created in the tree. Now you're going to apply material to it. We can do that here. Apply material, you can also find it here, or you can go back to the part design. That's entirely up to you, makes no difference. So I'm going to click on this, apply material on. Even if I selected this, because the joint is selected, it puts it on the whole thing, okay? And we say, it's made out of steel, and then we say, okay. In the event, let me see for a second, steel, let me see, where is steel? Right there, the part, we say, okay, or the joint, it makes no difference. Now, if you want to change the numbers here, double click on this thing, please notice that I'm not going to do that. But actually the problem says 30, so let me make this thing 30. So I'm changing this, taking slightly different values from what's in the database, and Poisson ratio 0.3. And I know don't need the stuff below it, therefore. So I'm using exactly what is given in the statement of the problem, which is right there. Okay? Fine. Now let's save this thing. We now go to analysis and simulation and generative structure analysis. Okay? I can go there to do some fancy meshing, or certain operations, certain things can be done here that cannot be done there, including that. Notice that in the agenda, I said, including external points to mesh must be in the advanced meshing tool. If time permitting, if we have time, we're going to do that. Otherwise, next time. Anyway, so I'm going to go to analysis and simulation, generative structure analysis, not advanced meshing tool. This is what I refer to as AMT. No. So it says that the default is static, fine, and there's nothing to do. Like in the previous 4 lectures, as soon as we created a solid model, as soon as we went there, it meshed it. But in the case of beams and shells, as you see, you won't do it. You have to do it yourself. So how do you mesh it with beam elements? Okay, let me bring this toolbar down. You're familiar with this. Model manager, the traffic light, remember that? The very first icon, notice that it gives you 3 choices. Tetrahedral mesh, which in the past 2 weeks, it has been done automatically for you, as long as you have a solid object. Surface mesh, which is a shell mesh, we haven't done that yet, and this is the beam mesh. You have to do the beam mesh yourself. You click on this, you select this thing that you remember, you joined, you put material on, you select that. It turns yellow, that's a good sign, and it says what size element you want. Now notice that this whole thing is 8. You know what? Let me make this thing 0.5. Maybe point, yeah, point, point 3. I'll make it 0.3. And then we say, okay. And notice that this is put in the tree. And by the way, there are 2 types. This is the linear type 2 node. This is the parabolic type 3 node. Let's not worry about parabolic one. And if you want to see the mesh, you can do that. You put the cursor on this line as before. You say right click, mesh visualization. You say okay, and look closely. Let me zoom in. Here is element number 23 going between whatever that node is. I can't see that. Node 1 and 26. Element number 22 goes between nodes 26 and 25, etc. Element number 16 goes between nodes 20 and 21. Over here on that pen, element number, I can't read that thing, but whatever it is, between node 26 and 28. Okay, so you get the picture. Nothing fancy, nothing fancy shows up. The rest of the problem is the same. You right click, deactivate. There's nothing I can do. Now, I have to tell the software what the cross-section of this wireframe that I joined is. Now, that is done here. You see that model manager, traffic light? You're already familiar with the first 2 icons, the first 2 set of icons. This one we never had to do because it always did it for us automatically. We always had in the past 2 weeks, we had 3-dimensional object. It meshed it for us with tetrahedral element, and it did it automatically. It put that thing automatically there. This is for shells, which we're not dealing with right now. And this one is 1D property. You click on the 1D property. Look at the shape of this icon. it says, it shows you an I-beam. So that means you're on the right track. You click on it. It says, okay, only property. What is the support? The support is this joint. Let me tell you, if you had not joined this, there is no way you can select this support. Okay? Or, yeah, you can try. Notice that the property, the material was correctly selected. Okay, right there, steel. And the cross-section type, there are many types. The one that we have is a cylindrical beam. And if you click on this wrench, it says the radius of the cross-section is based on the information that's given here. It says radius is 1, so I'm going to say 1. And we say OK. Here is circle of radius 1, which represents the information about the cross-section. Okay? Very good. Now, notice that we can close this. Without selecting the orientation point, we can close it. If this was not circular or tubular or cylindrical or tubular, we will not even be able to select this. We will have to create or select the orientation point. What we don't here, we can just close it. Okay. As before, let us go and save our analysis. So File, Save Management. Here's the analysis, save as, in that same folder, which was called bench rod with beam element. I'm going to put my analysis file there and say OK. Very good. So now let's go ahead and apply the restraint. Restraint, click on the clamp. This bottom is clamp. So let me zoom in so that you can see it better. Right there. The bottom point is clamp. Nothing else. So, okay. And over here, there is a force applied, a concentrated force. Now, force, when you apply forces in Newton, pound, etc., it's right there. Okay. You click on it. You select that point in the proper direction. That's not the proper direction. It's in the direction X minus 2000. And of course, this is 0. And there we are. You can see that right there. That's the direction of the force. Okay. Let's not worry about this handle point because nothing critical and we don't use it at all. So save everything and run it. Run means compute. You click on it, say OK, just give it time. Yes, it's very quick. Done. These are so efficient and it takes no time. Okay, notice that I can plot the deformation. You click on this and you can animate it. That's the way it should be. This point is climbed. This is subjected to a load. Incidentally, anything that you don't like, you can hide. For example, these properties, remember these cross sections? You can hide it. Don't delete it. You won't be able to delete that. You can delete this, but I'm hiding. Good. So animate this now. You can see it better because those were obstructing your view. Good. So it is acting the way it's supposed to. Now we're going to look at number. You click on that. It tells you that the biggest displacement is here, 0.03, almost 0.04 inches. Good. In the direction X. Look, you cannot plot the von Mises stress. You cannot plot this. It's rather unfortunate, but there's a reason behind it. Because von Mises stress is calculated at a point. And notice that along the cross-section, every point that you take has its own von Mises stress. Anyway, CATIA will not allow you to plot the von Mises stress in beams. Simple as that. Now, if you don't want these arrows as rendering style, so double click on it either from here or from the graph that you generated, entirely up to you. Either here or there, because these are the same thing. Double click and say average ISO, and there we are. Biggest displacement over here. And of course, smallest displacement is there, which is pretty much 0 because it's flat. Good. So let me save this thing. What is it that we can plot in addition to displacement and deformation? If you go here, you can plot the principal stresses, but the problem is that the principal stresses, just look, it only gives you the axial ones, only the axial principal stress. And here, in fact, because look, let me move closer. You can see that right there, very small. Axial stresses are very small. This problem really is not an axial problem. It's actually it's a bending and torsion. See all these principal stresses that are giving us are all the axial principal stresses, which is useful for the type of thing that we have. I'm going to delete this or deactivate it. Let me take a quick break. Okay, what I want to do now is to show you what happened is the cross section is non-circular. Obviously, if that is the case, then the orientation of that cross section matters. So to do that, I'm going to go and create a rectangular cross section, and I make a big aspect ratio so that of the cross section big, so that actually you can see what's going on. Let's go back here to our analysis, and what I can do is, just so that you have a review of this one more time, I'm going to close this analysis file. Oh, we already saved it. The part file is still there. Okay, so what I want to do is go there and create three points. Okay, so I'm going to create 3 points because I want to show you what the effect is when you choose these different 3 points. So let me go ahead and I am in for example generative where am I? I'm in this is advanced. This is wireframe and surface design. I am in that tool bench. Okay, wireframe and surface design, and here's the icon, wireframe and surface design. Okay, so I'm going to create 3 points. The 3 points are in the XY plane, but with 3 different coordinates. So let me click on point here. One of them is going to be maybe 3 inches in the X direction, maybe 2 inches away. Here, you can see that? It's right there. You can see this? Another one is going to be 2 and 2. So right there. And another one, 0 and 2. So I created 3 points because I want to show you what happens. Cancel that. Let me see what I created. One of the first one, or one of the second one, the third one, that was a mistake. The fourth one I'm going to delete anyway. Third one, coordinates should be 0 and 2. So there we are. So we have point 1, point 2, and point 3. Okay, let's save everything. We have already joined it, you can see. So now I'm going to go to wherever I was before, analysis and simulation, generative structure analysis. We will use the beam measure right there. See, remember, model manager, first icon, 3 possibilities. This is a tetrahedral element, shell element, it's called triangle measure, triangle, and beam. This is what we use. Click on this, select this, and we use the same number. You say, okay. So right now, it is the same mesh. The cross section has not been defined yet. So to define the cross section, you have to define a 1D property right there. You see this? 1D property. 2D property is for shells. We haven't done it. 3D property, if you want to mesh something yourself, but if it's done automatically for you, this is automatically created. But anyway, we're dealing with beam. Click on it. Now, I don't want, well, first of all, the support is this whole thing, but I don't want cylindrical. I want rectangular. And the size of that cross section, you click on the wrench and you give it a size. So just so that we can see it on the screen, I'm going to make in one direction 1 and the other direction maybe 0.3. You see? In fact, to make it even more dramatic, I'll make this thing 2 and 0.3. You see? Now it won't even let you close it. It won't even let you close it because you have not selected the orientation point. No, right here. No selection. You select this. Let's choose 0.1. Watch what happens to this cross section where I select point 1. It turns it so that it looks, kind of like that. Yeah. If you select a different point, it turns it again. You can see that. And finally, if you select this point, it changes the orientation. The moral of the story is just, if the cross section is rectangular, there is more work you have to do, okay? Because the orientation of this is important. For a circle, it doesn't matter. But the rest of it is the same. I'm going to, for example, clamp this, apply a load there, and run it. Of course, the numbers are going to be different, etc., etc. The moral of the story is that if the cross section is not a circle or a hollow or concentric circles, if it's not a solid cylinder or a hollow cylinder, you have no choice but to define an orientation point, and you have to do some work so that you get the correct one. Now, this is not random, but right now, I mean, you might say, well, which point do I use then? How do I create that point? That is not random, but you have to understand the significance of the orientation point. Okay, if all our beams are circular in cross section or hollow tubes, it makes no difference. Okay, you don't have to worry about it. Okay, so basically, I have done from this agenda, I did problem part A, I talked about B, and obviously we looked at part C. Part C is we look at it, if you double click on properties, double click on this, and you choose a different type of a cross section, maybe T-beam, maybe U-beam, you have to put more data in it, or even I-beam right there. Notice that you click on that, it gives you the information about, oh, this is thin I-beam, I don't want that. Let me see if I can find something. Let's see now. Thick, thick, thick. Well, for example, if you look at the something else, maybe we already did the rectangular one. Let's do the thin box. You see that when you click on this, it asks you to put some stuff in there. Okay. Well, I'm not going to worry about that. The point is that the kind of cross section is set here, and that takes care of this. So what I would like to do is to go and solve another problem for you, and that is this problem, and I'm going to use the plane of symmetry that are available. Okay. First of all, let me get rid of this. I don't want that. I don't want this. Okay. So what we have is a hoop which is hanging from the ceiling at the pin location. Okay. And somewhere here in the middle, exactly in the middle, I'm applying a concentrated force. Okay. And the value of it is 100. So you're told to use planes of symmetry that are applicable to beam elements. By the way, if this problem is given to you and it says use the most appropriate element, you will have to use beam elements. Okay. Most appropriate element for this problem is beam element. Now, so the plane of symmetry is xz. If you cut this thing into half, exactly the same thing happens on the left side is happening on the right side. Okay. That being the case, you don't have to model this whole loop. You need to model only half of it. You might say, okay, but if the cross section is circular, can I not, for example, cut it with the YZ plane? The answer is no, you don't cut a beam element so that you split half of this thin, slender member one in one direction, the other one in the other direction. Okay. So although if you were doing this thing as a solid problem, YZ would be applying a symmetry, but XZ XZ is the only plane of symmetry if you're using beam elements. Okay. Now the other thing is that when you cut this thing, for example, if you cut it with the XZ, because we told that that's a plane of symmetry, that is this line. It says when you do that, when you cut it with the XZ plane, it cannot move in the direction Y. So in the direction Y, it is 0. These two are free, and rotation is exactly the opposite. So if something is free for translation, is 0 in the rotation. If something is, again, free in translation, 0 in the rotation. And if something 0 in translation, free in the rotation. So this is the table that we're using for symmetry in beams and shells later on. Okay? Let's look at the last row. If XY is a plane of symmetry, no displacement in Z, translation in Z, rotate, and translation in the direction are free, and rotation is exactly the opposite of that. If this is and this is free, this is 0 and this is 0, and if UZ is 0, theta Z is free. Okay? All right, so let's go ahead and do this problem. The median cross section, the median uh, circle is right here, which is or is 10 inches, and of course the cross section diameter is 2. So this is 10, and this thing, this little piece is the diameter is 2, but this little piece is 1. Okay, let's go ahead and do that. This is a planar sketch, planar curve, and therefore we can do it in sketch and then proceed that way. Or you can do a circle in the or half a circle in the space, not as a sketch, and then proceed that way. But I'm going to do it as a sketch. Okay, I'm not going to do it in space, at least for this problem. I'll not. All right, so let's go ahead to the CATIA. You click on the uh, this pad, and you get your part, select your part, and immediately I'm going to save this. So file, save management, save as. I'll go one level up. I think it was bench rod with beam problem, so I'm going to call this thing hoop. What is this? Hoop, please. Hoop. Okay, this is without with plane symmetry, with symmetry. Symmetry. We can do that thing while we're in wireframe and surface design, or if you want, you can go to part design. It's not necessary because we're going to have to come back here. We need to join operation. You notice that I am in wireframe and surface design right there. So on the vertical plane, we will sketch. Why don't I do half a circle? Because we're doing half of that because of the symmetry. And the radius here is this radius of 5 inches. Actually, sorry, the radius is 10 inches, right? I think that's what we have here. Radius is 10, because this thing is 10. And we say, okay. Now, because the cross section is circular, I don't need an extra orientation point anywhere to create. So exit, don't forget to join. Join, join, join. In the operations toolbar, you select that. You say, okay. Now save this. Now we're going to apply material to it. So where is apply material? Right there. You select this piece and you go select the steel and you say, okay, if you want to change the values, you can go here to analysis tab, put the numbers that you want. In fact, in this problem, I think once again, I say that Poisson ratio is 0.3 and Young's modulus is this number. I'll leave it the way it is. I'll leave it as default value. Please, on the test, do whatever you're asked to do. You should go ahead and measure it. That's fine. 0.3, I'll make these things maybe, yeah, 0.5, 0.5, fine. Right click, mesh visualization. You can see the elements are linear elements. Okay, good. Deactivate that. Now we're going to apply 1D property on this. It selects the proper material, and then we're going to change this thing to cylindrical beam. You click on the wrench and you put down radius of 1. I think the radius is 1, isn't it? Radius is, your diameter is 2, radius is 1. And then we say OK. And notice that it allows me to close this without even picking orientation point. Right here, you can see this. Good, good. Now, these 2 points are in the XZ planar symmetry, right? In the XZ planar symmetry. So you click on user define, select this point, and you select that point. And these are both in the XZ plane. That being in the XZ plane means in the global coordinate system. Make sure you have global here. The reason it was user here, because last video that I did, I had to create a user coordinate system, but it remembers, unfortunately. So global, you select these 2 vertices. They are in the XZ plane, no displacement in Y. If they are in XZ plane, no displacement in Y, rotations are exactly the opposite. So if this is unchecked, this is checked, and this is checked, and in translation in direction 2 is fixed because of symmetry, and therefore rotation is free. And then we say OK. Now, so this is fine. This is good. And here we're going to apply a downward direction, downward force of, do not forget, downward force of 50 pounds, not 100 pounds, because we're doing only half of it. Now, I'm going to tell you something that may or may not be obvious to you. Look at this pin configuration. This pin configuration, it tells you that it cannot rotate about the z-axis either, right? Because if this is symmetrically pulled down and this is a pin, it cannot rotate about the z-axis. So this last one, I'm going to do another one. So I'll do another user define. And just so that remember, I say no rotation about z. Okay, so that same point, and no rotation about z. Obviously, these are already fixed. Because of symmetry, that was the case. So I'm going to uncheck all of these and say no rotation about direction 3, right there. This is fine. No, this point does not move in the direction 3 and does not rotate about direction y. And then we say, okay, essentially that point has become pinned. I could have clamped. Essentially that point has become clamped, because look at it. On the one hand, you have these, fine. And on the other hand, you have these, okay? All right. So, yeah, the force at this point in the z direction, minus 50. Okay, let's save our analysis file, save management, the analysis, save as. This is the folder hoop with symmetry, very good. And let's run it. Let's run. Okay, so there's something that's not properly recited. Let's find out what. Can we figure that out? Say okay. Can we interrogate this so that we can see what's going on? So let me click on the displacement. Okay, and let me go ahead here. Let me actually. Oh, right there. You can see that right there. Let me actually do the following. Instead of displacement, let me plot some. You know what? I'll tell you. the background is causing a problem. It's right there. You can see that. Okay. So, but I don't know what's going on. So I'm going to go to tools options, under the display, under the visualization. Let me change the background color. There we are. You can see this, and you can see what happened. If you animate it, you see this is moving as a rigid body right up there. So I have to take away that displacement in the direction X. You can see that. So let me go ahead and do another one. I can deactivate this. Let me go on another user defined. So prevent rigid body motion. This point does not move in the direction X. Good. Now run it. This time it should go through. Yep. And if you look at the displacement right there, let me change the color. The color here, double click, average ISO. There we are. And if you look at the view from the front, so that you can have a better idea what's going on. Okay, if you animate it, I can't see it moving because I have to reset the scale. So we go here, default scale, and there we are. You can animate it now, right there. And because of the conditions that I put in there, if you look at the side, it will not go to the left or the right. Now remember, I had to come back and avoid that rigid body motion at the top by, looking at why it bombed out. So there we are. All right. And this is it. You cannot plot one meter stress. You already know that. You can plot the principal stress, but unfortunately, it's very kind of useless because it just gives you the axial stress. Obviously, the biggest axial stress is right here. So what I've done is everything except that I was unable to go to this item D. And therefore, because of that, essentially, I have not done this thing with and without planes of symmetry. I've done it with plane of symmetry, but not without the plane of symmetry because there I need this last item. We're going to do that on Friday. All right, folks? Good luck.